speaker of the day, I would like to invite Dr. Kamal Shahid. He's working as an assistant professor at the Institute of Electrical, Electronics, and Computer Engineering, Punjab University, Lahore. Dr. Kamal's research focuses on digitization of power grid, the role of communication networks in smart grid, and the impact of networks on remote access to dynamic data of the distribution collection of the information. He is also a part of Danish as well as European Union research project related to smart grids. He will be sharing his thoughts on digital distribution grids and microgrids, status and challenges. Please give a warm welcome to sir. Sir.
Bismillahirrahmanirrahim. I feel honored and privileged to be here today. And for this, I would like to say a big thank you to the management committee of Comsat University. And specifically, I would like to say a big thank you to Dr. Shajil Wain Saab, Irfan Saab, and Mansoor Farid Saab for the nice coordination up till now. So thank you very much all. Do I have that pointer? Thank you. Yes. That's okay. So a few months back, I went to a dam, a famous dam here in Pakistan. I will skip the name. So I went there with my students, and I was given a chance to go into the control center inside. And I was surprised to see that there was a bunch of dozens of meters installed there for the measurements. And to my surprise, all the meters were analog meters. Okay, so while we were having discussions, there was a man who came behind us, an old man who just came with a register in the hand and started noting the measurements on each and every meter there. So keeping this in mind, while discussing this sustainable technologies and modern energy and a roadmap towards green economy, a modern green economy, I think it's very important. I think it would have been injustice that if we skip a very important topic, which is the digitalization of the grids. So I'm again thankful to the management committee, Dr. Shadil Saab, for keeping this topic, this hot topic here in this the series of presentations, the series of lectures here. So what I'm going to present today is related to my work and what I did in a 3-year project in Mark. It was a European project, 3.5 years project that we did in from 2018 till 2021. So I'll be talking about digital distribution grids and microgrids status and the challenges that we faced during the project. The project name is okay. So the name of the project is leveraging network data for the digital electricity grid. We call it, it has an acronym which is net to DG. I'll be taking this name net to DG off and on. So you should know that this is the abbreviation of the project, and the extension of which is leveraging the network data for the digital electricity grids. And there were different partners in the project. It was my university, Aalborg University, Denmark. There was another university from Austria. It was Technical University of Vienna. We had a software development company called Grid Data. It was from Germany. Kamstrup is a very famous smart metering developing manufacturing company there. And it was, again, we had a software development company, called it was PV inverter based company called Fronius from Austria. We had a software development company called Resultech, and there were two DSOs, distribution system operators, and in Pakistan we call them DISCOs, whereas here in Europe they call them DSOs. So this was the whole consortium there, comprising of 8 partners, and this whole project was for 3.5 years. So to begin with, I would just tell you a few things about the electricity grid that are almost common with what we have in Pakistan as well. In Europe, in most of the Europe, especially Germany, Austria, and all the Scandinavian countries, the electricity grids are operated by these DSOs, the DISCOs in Pakistan, distribution companies. And mainly what happens is there is a power generation center, a centralized power generation center, which produces electricity, transfers that to the primary substations. And then from the primary substation, it goes to the secondary substations via the medium voltage grid. The medium voltage grid in Europe, it's 10, 20, and 30 kilovolts, whereas in Pakistan, it is 11 kVs, where they have different consumers, large consumers, big generators in the range of medium voltage range. And the secondary substations connecting to the low voltage side of the grid. And then from this secondary substation, the electricity moves on. It is transferred to the low voltage grid. From the low voltage side, again, as in Pakistan, it is distributed to your homes, your companies, or whatever, wherever the electricity is required. And yes, in most of the grids in Europe, I think in Pakistan as well, they are also, again, there are radial topologies. So the same is the case there. So what actually are the targets of the DSOs, the DISCOs there in Europe? Again, as in Pakistan, it is the main purpose is the availability of the power supply. They are also meant to provide a constant voltage quality and a specific efficiency of the electricity, and then increasing, decreasing, and controlling the hosting capacity. It also lies under the responsibilities of the DSOs, the DISCOs. Okay, so when we talk about the centralized power production, the things there again are connected. They are highly connected, but the problem is now the system is changing from centralized power system to decentralized power system, where we have distributed generations, like we have solar PVs being installed. You might have observed the place where I'm staying, Comstack. You can also see solar panels installed on top of it. Many homes they are having solar panels there. We have wind power supply, wind power production plants. While traveling to Karachi, while traveling to Sindh, you might observe that there is a huge plant, wind power plant there installed. So from the centralized power system, the things are becoming highly distributed now. Now, in this scenario, what happens when there is a fault occurs in this condition? Same as in Pakistan. What happens if there is a fault? The DISCOs, a network technician from the DISCOs will be handed over the responsibility now and see where is the problem. And he will go from different directions. He will move from here and there, and then finally he reaches to the point where the fault actually occurred. Now this whole process takes some time. This whole process takes some time. Why? Because there is either very small data available or there is no data available that would help you identifying the position of the fault. Not only the position of the fault, but also the type of the fault that has occurred. So there is no data available right now. So this whole process takes time, which might vary from minutes, not minutes, but hours. It might take a whole day to identify the fault, where the fault is. So this is not the whole story. What else, what more challenge do we have here? In spite of this rising integration of distributed energy resources, the solar power plants, the wind power plants, and so on, we have these new consumptions. As you might know, that the government has announced electrical vehicles will be coming soon in Pakistan. So that is also an addition in the consumption of electricity. We already have in Pakistan a mismatch between generation and consumption. So when these kind of loads are again added to the system, where would this gap be in the future? Similarly, we should have expensive grid investments to be replaced by intelligent use of this flexibility of the system. So this can be done by using the microgrids. And just imagine, by having this high number of distribution power plants generating electricity, and these microgrids operating at different places, this multitude of devices and grid elements increase the management effort. And last but not least, when keeping this in mind, we have very low distribution grid observability. How do you observe all this grid? Do you have the data resources? Do you have the data coming? Do you have the measurements coming out of somewhere? No. No means if there is some measurements, they're very small in number. So we have a partial or out-of-date views on the grid status, which hinders this fast reaction. First, processing of the fault detection and grid monitoring, etc. So what actually is the solution now? The solution proposed by Net to DG project that I just introduced in the beginning, the solution is to have more and more measuring devices installed at different locations of the grid. So what these data sources do, these data sources send relevant data regarding your supply status to a central data analysis unit. And what it does is it provides advanced information for the discos. It provides advanced information to the discos. And what it does is the data and the analysis help to better understand your energy status and can directly inform the network technician that where actually is the fault, where actually is the failure, and what to do about that failure. This is done by these measurement devices by sending the information to a centralized location. So just imagine that we have a lot of devices, a lot of smart meters, for example. There are meters which are digital meters, not digital meters, but they are smart meters measuring the information, measuring your energy status from your homes, collecting the information, and then sending it to a centralized location, centralized data analysis unit. Just imagine we have, let's suppose in a small town, we have 100 homes, which means 100 smart meters. If there is any PVs installed, let's suppose 10 or 15 PVs installed at that small town. So 100 plus 15 or whatever the number is. So this much devices, data sources that are collecting data and sending to a central unit. Now, keep just increasing the scale. We have thousands and thousands of homes that might, for example, if all these homes have these smart meters installed, they would have to send their data to a central location. So what happens? You have a multitude of complex IT systems containing relevant data. And all the data, it's not coming from only one type of systems. Like, for example, we were using smart meters from a company called Comstrup, whereas the DSO in Germany, They were using smart meters from some other company. So the data format, the heterogeneous data that is being collected from different places, that would also hinder in fast processing of the data. So there will be a disparity in the data quality and the formats due to this multitude devices that are being used. Similarly, what else? What kind of challenge do we have more? We have uncertainty about what and where to measure. Smart meter is one of the things that you can install at your home, but what else you can use to measure different, you have different measurements. And then the evolving grid structure and changing customer behavior. One should think of installing the smart meters at the homes. What happens? I remember, I'm not sure about Islamabad, but I remember in Lahore, when they decided to change from analog meters to digital meters, there was a hype. Na, ye na lagana. Ye bijli zyada, ye bill zyada aata hai inse. So what to do about that customer behavior? So you have to install new sources of digital data, but you have to keep in mind the customer behavior as well. So I said we need to use different data devices, data sources for collecting the data. What kind of data sources and what kind of information is useful for us? So the data sources in low and medium voltage grid, one of the important source of information is the geographical information system. I'm talking about measurements and then geographical information system. Why? Because whatever the measurements that are coming, how would I know that what device is sending this information? Like you have a Google map where you can see that where is your home. You can just locate your home. You can see the picture of your home in a big picture of the town. You can locate your home. Similarly, I should be able to locate that where the information is coming from. I should have a map. I'll show the map that we developed. We should have a map which shows that what devices are connected where. And how are these devices connected? I'm getting the information, I'm getting the measurements from which device. I should be able to do that. And this information is done by having geographical information system, which we should have grid topology and the component data, what is located where. Then we have customer size where we can have inverters, smart meters. Inverters, you might know that whoever installs these inverters, they have net metering. Most of you know that what is smart metering. So the information, the measurements are coming from there. And similarly, we can have some electrical or power quality measurement devices, which can be stationary, which can be mobile, which can be used anywhere in the system. Apart from that, although we don't use these in our project, but we have the opportunity, we can also use component-based sensors like circuit breakers, temperature sensors, and many other things into the whole big picture. Similarly, some PMUs can also be used to get the measurements. So, do you think it's just as simple? It's just trivial that we just take the smart meters, install it on the field, and then get the data and do whatever we need? No, it's not that simple. What we need to do for this is we should first have a digital twin. We should first develop a digital twin for the distribution grid operation and the planning. You first develop this. Once you are successful, you move on to the field. So what are the expectations? What are the challenges that we have here in case of digital twin? The first thing is that we need to integrate the distribution grid data from existing and the future data subsystems. Whatever we are installing, I'm not sure that in the future someone from outside comes and install a new device. So my system should be resilient enough to cater that new device that is connected to my system. What else? It should link the measurements data to the distribution grid topology. As I just mentioned, grid topology, it's very important. Where are the different things connected? So the information coming, the measurements coming should be mapped to whatever the device is connected. We should build consistent distribution grid models, which actually represent the reality, the field, where everything is installed. And then we should deal with once everything is done, we should deal with the uncertainties and missing or inconsistent data. What are the causes of this missing or inconsistent data? I'll just get back to that in a few minutes. So what we developed here, it was this kind of a structure. It seems quite complex, but I'll just explain you what is this. We are collecting we collected measurements and data from different devices. We call this headends. Headends are the component that collects data from different sources. So first of all, as I said, we need topological information. This topological information is obtained from this topology headend, which is responsible for collecting information from different topological data providers. Like for example, the discos, they already have the information that where things are connected. In our case, we were using the information from, sorry, we were using topological information from two sources, two DSOs, two discos. One that was in Denmark, and the other one was in Germany. From Denmark, whatever the topological information we obtained, it was totally in a different format. It was an XML file in a model called Common Information Model. Whereas in Germany, whatever the data we collected, that was the topological data that was in the form of XLS files. So both were different. So what is the purpose of this headend? The purpose is to convert that topological information, whatever the format is, it just prepares it to be used by this central unit. I'll come back to that. Similarly, we have this AMI, the advanced metering infrastructure, where it collects the information from the smart meters, gathers that, converts that into a format that should be usable by this guy here. Similarly, inverter headends, electrical measurement headends, and whatever. There were different data sources that were collecting information, converting them into a format that should be used by this guy. The central guy here is the analysis unit, which analyzes all the data, saves the data into a common format that can be used by different applications here. It stores the data into the databases. Now, from here, we call this data fusion hub or ICT gateway in terms of, in case of net to DG project. So this data fusion hub, what it does is it captures all the data into the database. Now, what to do with the data? There are different applications on top of this, and there is a GUI, a graphical user interface for you. I'll show you the picture of that. So what it does is there are different applications like grid outage detection. I need to know that where is the outage. This guy here will request the data fusion hub that please send me the information, whatever the measurements you have. This guy here will send the information back to this application. In case it does not have the information, it does not have the measurements, it will just request any of these guys to send the information, send the measurement, and then process it, provide that back to grid outage detection application. And this will know that where actually is the problem. Similarly, we have grid outage diagnosis, we have earth fault localization, grid monitoring. You can monitor the voltages, the powers, currents, energies, etc. So all applications are meant for having the insight into the grid by using the measurements, by using the data you already have into the database. So what actually is the purpose? Since the time is short and I need to run, so what actually is the target for all this process? The target is that we should calculate the outages. And what actually is meant by the outage? It is a loss of ability to deliver demanded electrical power to a point or position in the electricity grid. It can be due to different things. So in order to measure that, we have certain interruption indices like SAIDI, System Average Interruption Duration Index, which is calculated to see where were the different the interruptions or the outages were occurred at some point into the grid. For example, here, this is the map that I was talking about. We have a map, a location map, where you can see the location of different meters, for example. So there is a substation. A substation is connecting different customer connection boxes. Customer connection boxes are something that has these smart meters installed, and you can get the information from these smart meters. For example, there is some issue into the grid. You can, by visualizing this into a graphical user interface, you can see that the lines here, which were blue previously, they become red. And becoming red means there is some problem. And then you can access the data from here and see where actually is the problem. So what are the challenges? What are the challenges in detection and diagnosis using heterogeneous measurement subsystems? There is a huge lot of measurement devices, measurement systems that are sending the data, but you have to use the data in certain single format. So the first thing is the measurement data accessed through different IT subsystems. And for example, one of the systems is the AMI system. When talking about the AMI systems, there are different smart meters. Different companies are installing smart meters. And I was working with the smart meters manufactured by Kamstrup. Whereas while returning back, I contacted one of the companies here in Pakistan, which are also developing smart meters. They provided us those. And believe me, the format they are using here in Pakistan, it is totally different from what we had there in Denmark. So the first thing is the format of the measurements that is being saved. And then you also have the request strategies of the meter data management system. How would you access the data? Is it periodic data access? Is it event-based data? How would you collect the data? That is also one of the challenges. And different possibilities are for on-demand requests for the smart meters, performance behavior of the communication solutions. Would you be using a single communication system for all the system? No. Of course, there would be different kind of communication systems involved here. Some might be using LAN, some might be using wireless communication, and all these, a combination of all these will affect the overall performance, can affect the overall performance of your system. Similarly, the meter types and meter configurations, for example, push notifications, you are pushing the information you are asking the information from the smart meters, and it is sending the information based on your request. But for example, if there is some event that occurs, there is some failure or something, it will send the information directly to the AMI head. So there is one example called last gasp. Like, for example, if there is some problem into the smart meter and it's just going to die in few moments. So before dying, it will send some alarm to the central unit. So that alarm cannot go in with the normal data. It has to go directly without any delays to the central administration unit. So there are different things that we need to take care about while, for example, considering one subsystem, which is the AMI subsystem. Now, again, what can be the target? The target is to attain a specific efficiency of the grid. In Europe, on average, more than 7% energy loss is there in the local distribution systems. Do you know anyone from you? What is this loss here in Pakistan? According to this NTDC, in 1920, the year 1920, it was 20.120, which is quite high. So what actually are the causes of these losses? It can be, there are different losses. For example, there are technical losses, which can be variable, which can be fixed. Variables are due to the lines, cables, etc. The fixed losses are due to the transformer core. And all these losses can be influenced by different things. I'm not going into the details, but all these things combine together to add up to the losses into the system. Okay, so what other challenges do we have in fault calculations? We have error measurements in smart meters. We have a legal requirement of ±2. It was in Europe, and here again, when I got these smart meters for my calculation, for developing the system here, I was also told that don't rely on the smart meter measurements. You should first check either the smart meters are fine, are accurate or not. So this is also one of the issues that we cannot just rely on whatever is coming from the smart meters. Inaccuracies in the measurements. As I mentioned, we will have hundreds and thousands of smart meters or devices sending the information together. All the measurements, do they have the same timestamp or not? A little mismatch in the timestamp can also cause errors into the measurements. So this is also we need to take care of. And then the missing measurements. Missing measurements, what are the causes of the missing measurements? There are different causes. They can be different causes. For example, lack of measurement devices, measurement device fault, the device that is sending the information that was faulty. There can be an issue with the communication system that you're using, the network that you're using, some legal or privacy issues. In Europe, we have they have general GDPR, general data protection rules, by which you cannot access all the information coming from the home. So you have to be very vigilant in collecting the data, that what data you can use that is coming from the homes and what is something that you cannot use. Similarly, once things are legalized here in Pakistan, they are formalized in Pakistan, we would have certain rules that what data we can use and what not. So this also hinders in collecting the measurements. And what happens if we have some missing data? What do? We can calculate or predict the missing values. There are different tools by which we can calculate or predict the data. Like, for example, we can use the historical measurements, interpolation or whatever, different tools we can use. We can use the data from the grid models, like, for example, power flow, state estimation, etc. We can use that to get measurements, missing information. But what are the challenges? The challenges are quantification of the errors of calculated values required. And similarly, the grid model requires grid topology or the characteristics. If you don't have the true picture of the grid topology, believe me, I'm the witness that we had huge losses there in the system. Now, just a little bit more about the grid topology. What actually do we mean by the grid topology? It means that we should have geolocation of the transformers. As you can see, the exact location, the x-axis and the y-axis of your home. Similarly, you should know the x-axis, the exact location of the meter of the device that is sending the data into some graph. Similarly, where are the different junction boxes lie? Where are the different consumers and the producers lie? This is something you should know. You should also know that where are the cables, where are the different lines between, what is the length of the different lines between different customer connection boxes, different homes, etc. That you should know. And what we witnessed, what we experienced while collecting this information, we saw that the cable lengths in the building, they were not appropriate. Usually they don't care about that. Vertical cable lengths were also a problem. Information about the parallel cable status and the placement of the breakers. This whole information is required to have a big picture of the monitoring of the grid. And there are different approaches by which you can get the data. For example, you can use metadata to quantify the uncertainties, estimate the uncertain or unknown topological information from the measurements. So there are different ways that you can use to get this information. So finally, if we summarize the whole concept of the digital twin, coming back, what actually do we require here? We require a system that has the ability to integrate heterogeneous data through modular and scalable architecture. It should be modular. Different modules are sending the collecting the data and then sending it to some centralized unit, a brain that analyzes the whole data. And that should also be scalable, so that in the future, if some more systems are to be installed, it should be able to cater this. Then we have accurate grid insights despite missing measurements and erroneous data. This is possible using accurate grid topological information. Once this is done, we should optimize the operation and planning using those existing grid infrastructure. And finally, once all is done, we can also use everything using this effortless setup and ease of use by enabling AI and the cloud technologies. Once we have all accurate information, this is one of the possibilities that we can employ this AI and other things to use it in the future. So the goals of the project, what were the goals? The goal was to reduce this time to outage diagnosis by 70%. One of the targets was to reduce the grid losses by 10%. Anticipation and mitigation of 60% of the upcoming voltage quality problems was also one of the targets here. Reduction of low voltage grid enforcement investments for increased hosting of DERs by 30%. This was also one of the targets. And what was achieved was that our outage detection and diagnosis time was reduced to few minutes, which are according to the results that we obtained by the end of the project. The grid losses were reduced by overall reduced by 11%, while the voltage management applied in the combination with continuous voltage monitoring and different applications that we were using. Similarly, the hosting capacity of the field trial we had in a grid in Denmark as well as in Germany where we applied all this, and we saw that there was an increase of by 30%. The hosting capacity was increased by 30%. And yeah, there were other things. There are many other things that I wanted to show, but of course the time is limited. So what I would request you that you can go onto this website, net2dg.eu. You can see different reports, different deliverables, and the papers that we have published during this three and a half years of span. And yes, you can just go through the different achievements what we had during this whole process. And for your information, soon after I returned, I'm thankful to Dr. Sobia Beg, the head of Energy Department in Comsat University, Lahore campus, that we have proposed the same kind of project here in Pakistan as well. And when we are still waiting for the approval, hopefully. So yeah, this was all from my side. Any questions?
Thank you for a very interesting talk. You mentioned this problem about non-uniformity of the data formats. So I was just wondering, are there no IEEE standards that govern the format for the data, or how the communication should take place in smart grid? And if not, then what is the stage of development of such a standard? I mean, are there working groups and so on and so forth?
Thank you very much, sir. Yes, there are different standards. In Europe, we were following IEC standards. And the next stage after doing all this was to convert all that to basically move on to the standards that are being set. So smart grid, there are different standards they are developing. And especially for collecting this data, we have different formats. Like I mentioned, one of the formats which is called Common Information Model. So one of the targets here is to convert all the data that we have, specifically the topological data. It should be moved from any data like is it in Excel files or whatever. It should be moved on to a common information model. So people are following that basically. I saw one project in Europe that was totally based on converting the data to comply with these standards, which is IEC standards in Europe. So of course, here in in Pakistan, in Asia, we should follow IEEE standards. So yes, there are cases where we have to comply with these standards.
What I like to say was that for this case of Wi-Fi, you have this branding of together and compliance, so on and so forth. So in the case of these devices that we put on the grid, we don't have to, comply with certain standards. That in the modern day, the
Apparently, yes, it should be solved, but as our experience, as I experienced, it was not the case. So I'm just talking about. I'm not talking about the communication problem. The first problem is to collect the data. So once the data is collected and then it is converted into a format that is usable by these standards, then it should be okay. But the main issue is the data is not compatible right now. So the first issue that needs to be resolved, that should be addressed, is to convert the data that is usable by whatever IEEE standards or whatever. So
I have some question. If I have understood properly, I think your project has nothing to do with the communication of the data, collecting of the data, but your work or your project is related to analysis of the data. That already the data has been collected into a place, and then that data has been analyzed for different purposes.
well, we started, it's not the case. We started from the scratch, that we had no idea where to collect the data. The first issue was to address this data collection first, the topological data, the smart meter data, and different sensors data that we need to collect. So the first thing was to collect the data. And now the second step is to how to.
But that I mean that infrastructure is already there.
What infrastructure?
I mean, you know.
No, it was not there.
The
We had to.
network, the smart meters, everything is already there.
No. We had two sites. One was in Denmark and the other one was in Germany. In Denmark, they claimed that they have 100% rollout of the smart meters, but that was also not the case. The area that we were focusing, that had, it was having 90 homes in that area, and all those homes were having smart meters. But just contrary to this, in Germany, the area that we were focusing, they had no smart meters installed. So we had to install different devices to collect the data. And how to collect the data, of course, we need some communication system. Although we use this 4G, 3G and 4G network to collect the data by installing different SIMs and different devices to collect the data. But still, there were several issues that we faced while having the data. There's sometimes the communication network was in full peak, and sometimes it was congested. So we had missing data into the database. So these were the issues that we addressed.
So well, you know the main focus of the project, because the thing is, if you analyze the data for different, for example, 3-phase fault or single-phase fault or 2-phase fault, something like that, because already there is, you know, the existing technology is there for the fault allocation. So what was the problem with that? Because already that is working.
Yes, we have these applications already installed, but they are mostly at the high voltage side. Usually at the medium voltage side and the low voltage side, they're missing right now. Even in Pakistan,
distribution side is already there. And also the monitoring system is there. And the data has been, you know, collected and it is sent to a central station. And there is a mimic board, even in the distribution system I have seen in the UK in 2003. And all the data is collected and it is shown on the mimic board. You have the voltages, you have the power flows, you have everything.
Yes,
so what is the problem with that?
Yes, I agree. I totally agree with UK and in some states of US. They already have the system. But since it was meant for specifically for Germany and Denmark and Austria and some places in Austria, so there they were lacking this kind of system. Specifically,
by that I mean that the system already is there for the fault allocation, and also the data from the field is collected, and then it is shown even on the mimic board, and you can see everything there, even the state estimation, and the real-time power flow is also run. So what is the problem with the conventional system? Because they are already, you know, collecting the data and they have everything available, and they analyze the data and they take the decisions. Even the contingency analysis is done based on that data. Everything is being done already. So why you were shifting from that? What was the problem in that system?
To my knowledge, this whole application, this whole system is available above the medium voltage side. And below that, in the distribution system and in the low voltage side, the system is lacking. as far as I know,
visited,
in the
distribution
Scandinavia.
system.
So
We visited in Scotland,
Mhm.
a grid. which was
Scotland
in-
and UK, of course.
Yeah.
I'm not
And they
talking
have
about that.
everything there, and they have very good system, and
Yes.
they showed us
They also have
everything, and-
smart home system as well.
Yeah.
That I saw that there are different applications where you can control everything, every entity at your home. There are systems in UK, but of course that this system is not there in talking about Denmark, in Germany, in Austria. I didn't see any system like that. Even in the DSOs that I'm talking about, they don't have this system. I'm talking about some specific DSOs. There might be some DSOs. They don't have they already have the system, but the DSOs with which we work, they don't have that system right now. And I'm talking about this project that was developed it started in 2018, which means in 2018 there were still systems. There are still distribution system operators which don't have these systems installed. So they are developing basically. They're moving on to some modular and scalable systems, or there might be some issues that they need to address in the future.
So, did you work at the data analysis as well in that project? Or you didn't
Yes,
work?
yes, not me specifically, but there were different groups. Like there were two software development companies, one in Italy and one in Germany. They were doing the data analysis. I can also share some reports with you where you can see that what kind of data analysis they did and how the different applications were working there. I'll definitely share with you. You can also see it directly in this by visiting this website, net2dg.org. There are different deliverables that you can see how the different data was collected, how it was communicated, and then how it was used for different analysis.
Thank you, Dr. Since we have submitted the project, although I have some knowledge on this, just for the benefit of all others, I would just like to ask this that let's say we implement this system in Pakistan. What do you think the cost can be prohibitive, or can we replicate at least a digital twin, if not the whole process of it, and so that we can curb those T&D losses over there? So the cost benefit analysis, rather, I'm talking about.
Definitely. Like you already know, we have a huge problem of Kunda system, where you don't even know where actually this electricity goes, who is using this electricity, who are the consumers. So once things are digitalized, there would definitely be a clear picture of how much you need and where actually it is to be utilized, it is to be consumed. So once this picture is in front of you, there would definitely be a lot of cost benefits that you can see in the future once installed.
I'm Ahmed from Counselor's Electrical Department. My point is, your research is quite good, but the SCADA system of Pakistan, it's very reluctant to accept any changes. So my question is, what are your sellable points that allow you to penetrate in that system? Just give you an example, like whenever there is a fault come, so the system hold. And at the end of the day, they will come to know that that was not the fault that we have to hold for 24 hours. And you know that there's the loss of so many things. So if the system is good enough, that can detect the fault at the very early moment and let the grid on. So have you worked on that? So I think that you will work on it, because I'm working with this whole system. So my point is, what's the best sellable points you have in your mind to come to Pakistan?
Can you repeat the question, exactly the question?
Okay, what's the best system you have that you can penetrate? If I will compare your system with the SCADA system already, working on it to detection of all the faults, metering, and whatever is there. Because we have all the system, it's on board, and we can see where the problem is. But the smart thing is whether the fault detection and their implementation, because we allow the dam or any system to move on or to reboot, and it will take some time. But if you talk about the smart one, it will reduce the time and save the money.
As far as I have understood your question, in case of SCADA, you are collecting, although you are collecting information from different sources, but at that level, you are relying on high communication technologies, for example, fiber optics and some private networks. But in case you need to collect data from each and every home, not only a single home, but you need to collect information from different sensors being installed at a single home. You just imagine the amount of data that is being collected from a single home. We collected the data from 90 homes, and you believe me, my system was held just for after collecting data for 1 day. So the real problem, I think, as compared to the SCADA system and the system that we are going to employ here, will be that the amount of data that we are collecting, as Dr. Saab also said, that he saw some live data. So live data, of course, the definition of live, it varies in case of distribution systems, in case of SCADA. So this also is something that we need to differentiate between that system and this system, because here live data means you are moving toward big data analysis, and big data, that is something else. So this is one of the there are few differences that once you talk about SCADA and the information collection and analysis here at the distribution level, at the low voltage side. I hope I answered the question. So. Just you're right. We are not sending.
Control mean we can control the operation of the system. We can increase or decrease the load. When we know this information for the voltage and the current information, we can control the and if we are only considering the power demand or generation, we only need active and the reactive power information.
I totally agree with you. But when I said huge data, it does not mean that we are sending all the parameters that we are collecting.
Only if we are dealing with 4 to 5 IPPs,
yes, exactly.
It means it is very difficult to manipulate that data. And if that data is manipulated for only per hour basis, only per hour IPP is sending data to the WAPDA on per hour basis.
Yes.
And also to manipulate 10 to 15 IPP, it is very difficult. And when you are managing 1 million suppose user, it would be very, very challenging.
Yes.
And
so
IPP is only sending the active and reactive power information. When we will send more data, for example, voltage and current information, location, whatsoever that would be, it will be more challenging.
Yes, I agree with you. I agree. This is what we did. We are not sending all 220 or 230 or 250 parameters that are obtained from the smart meter. We are just sending few parameters, and those parameters are sent with the sampling rate of 15 minutes. So 15 minutes sampling rate, and they are collected after every 6 hours, for example, in some smart meters. They collect the data with the sampling rate of 15 minutes, and then they are sending to for example, a concentrator. So when I say huge data, it means collecting it from thousands of homes. So this is what I mean by huge data. Yes, exactly. So when Dr. Saab said live, so there are different definitions of being live we need to take care of. So what do you mean by live? It's not that something is coming and you're displaying it on the screen. So yeah, there are different definitions. Yeah. Thank you.
Ladies and gentlemen, the next speaker for today is Dr. Syed Abbas Kazmi. He is working as an assistant professor in the Department of NUST. His area of specialization are smart distribution networks, power system optimization and planning and scheduling, and power and voltage stability. He will share his thoughts about smart grid and smart distribution mechanism to enable energy mix. Sir.
I will try to concise. Thank you very much. Presentation. Thank you very much. Bismillahirrahmanirrahim. Assalamu alaikum everyone. I'm Dr. Kazmi, and I'm honored today for this presentation titled Smart Grid and Smart Distribution Mechanisms to Enable the Energy Mix. Oh, okay. These are the contents of my presentation. I will right away start with the introduction and followed by a smart grid basic concept. That is model of smart grid package, and smart distribution mechanisms to enable the targets which we are aiming at. Then the issues we have, the gap analysis and opportunities and way forward and future targets, followed by the conclusions. So I will right away start with the introduction, and that is regarding history of electrical grid, because the microgrid that we are today working with was used to be standard in 1882. It will be a fun fact for you. When the Edison just started the very first kind of distribution, and it was DC distribution. But later on, the war of currents was won by Tesla with his AC system. To start with, I would like to first of all show the current status of our distribution network. In fact, the whole power system. We have got a surplus generation. It's we had 40 gigawatt in 2021, which has been raised up to 42 gigawatt. And still our demand is at 28 gigawatt. And why we still have load shedding? Reason being, our transmission system was not reinforced properly. As you say, see by the same clear curve, the amplicity is low. Thermal limit hits first, followed by the voltage and then the stability limit. So to convert our system to a smart system, we have to reinforce each segment of the grid, not just single one. We have used to surplus the generation. We have got so much surplus generation, but it is not of that use to us. So each segment of the grid matters. Now regarding smart grid, well, the smart grid concept depends on the way you look at it. For sir, it might be smart meters. For me, it might be smart microgrid, virtual power plants. For a planning engineering, the planning perspective is smart grid for itself. And for scheduling and protection. So it's a system of systems, not just a journal kind of thing that we are looking at. And for sure, there are 7 segments of that grid. We have to go through one by one. So I would like to follow the NIST system because it was the very first from the director DOE America. So we have got 2 definitions of smart grid. There is not a universal definition of smart grid, but we go with the 2 definitions. One is of NIST, second one is of IEEE. IEEE says that there are 3 layers. It's system of systems. It has got 3 layers. One is power layer or energy, and the communication and ICT layer will support it. The main thing is managing it to the fullest potential. Our main commodity is power/energy, supported by ICT. So, in retrospect, what the smart grid actually is, it's basically ICT at the backup, electrical grid modernization with the asset optimization. Asset can be even sensors, it can be the DGs, it can be anything. Okay. And also the integration of new distribution concepts. What are new distribution concepts? We have a hierarchical system of the concept that basically I would like to show. This was the hierarchical concept, starting from generation, far away, the transmission, the distribution, and the utilization. So the future grid will be a bidirectional. Right now, our transmission system is reinforced, it's bidirectional. It is in a ring or match configuration, but not our distribution system. It's mostly radial. So if you have to convert a system to a interconnected one, you have to improve the or upgrade the protection system. Then the very classic impedance protection and all that kind of protections will be just part of history later on if you move towards the numerical protection and other kind of things. So each segment matters. So this is the first one. This is our current system. If you further see it, in past, the distribution system was considered to be the dumb one, the passive system, that it's consuming all the power and it's not delivering anything. But right now, we have got distributed generations. The net metering or reverse metering that you are working with it, what is this? It's a type of distribution generation. So this system is a little bit upgraded. And in future, we have got a whole package of functionalities, concepts, everything, which were limited in the current infrastructure. So the next model of smart grid, to start with this, first of all, we must know that why we are striving towards smart grid. What's the reason for the smart grid? Why we need it? What's the motivation? So the first of all is wide geographical spread. You see that the system, one of our respectable faculty members just said that the SCADA system of the NTDC, what it was used to be in 2010, it's almost double. And the whole graphic user interface and the mimic board you basically see there, it has been increased very much. Not only on the transmission side, but also on the distribution side. So this major load center, these kind of things, wide geographical spread is the first thing. That whether we continue the same streak as we used to do in the previous times, on the same SOPs that we used to make our substations and other thing, or convert it or build new ones which are better than the previous ones. That's the first thing. Then we have got large number of interconnections. That's a very problem that we are getting in net connections right now. So those large number of interconnections, either due to political, economic, and reliability, stability issues, whatsoever they may be. Then we have got rapid growth in the demand of electricity. Alhamdulillah, population is exploding, and so is our standard of living and development of townships. Means just 20 years ago, we don't used to have barrier or DHS or those kind of things. But now there is a mushroom growth of societies and everything. Not only on the residential side, but also on the industrial side, commercial side, there are various avenues. So how you will power them and how efficiently you will power them and how you can ensure the power quality that is mandatory for them. So that's another thing. Then power system components are being operated close to their design limits. So the very thing, our transmission system, it's very operated very close to its operation limits. And we can't move above 28 megawatt, right? So investment is needed for that as well. And the strategic reinforcement, not just reinforcement based upon kind of thing that just there is a PC1 and start doing it anyway. There must be some method to that madness. Anyways, high penetration of renewable energy resources. Now, they are subjected to the intermittent nature. But now we have got the technology. Now we have got the practices. Now we have got all those things, means in terms of lay coordination, system stability, everything. Uh, but for that, we have to reinforce our system. Means the ARE 2019 policy states that it must be 30% by 2030. But that 30% of the renewable is subjected to the reinforcement of all those infrastructures that are at hand with us. Then we have got competitive electrical market. The CPPA and PPIB are working towards that deregulated market. Right now, it's regulated. NEPRA buys all the electricity and sells it at a certain basket price. Then there will be a sort of board of director kind of situation in which NEPRA will be facilitator and rest of the people will basically, they have a competitive kind of arrangement which will ensure further good service. Then we have got generation. Right now, our generation renewable is 5%. If we even include the hydel into that, so it does not surpass about above 35%, right? And still 65% of our generation is thermal based. So just see in the retrospect that how much carbon footprint we are adding, although we are only responsible for 0.4% of the global carbon footprint, yet we are third most stuck country in future regarding climate change. Then we have got transmission system, but it also is subjected to certain kind of, it requires a little reinforcement. Also, with respect to energy efficient and monitor in real time, like a wide area monitoring system and protection against potential disturbance and optimal use. Then we have got distribution and utilization. So the one thing is that if we have to increase the DG penetration, and that too is renewable, so it is subjected to, first of all, our distribution system is unbalanced. To give you a perspective, for example, you have got three phases. In one phase, there might be 10 homes. In the other phase, it might be 15 homes, and the other phase, it might be 5 homes. So it's basically unbalanced. First thing. And the net metering is only allowed at for the 3 phase meters, which is only 10% of the whole meters. And still 90% of the meters is single phase. For example, if there is some policy that how to convert that one phase meters, which make 90%, and make a policy to bring net metering to them as well, then it will be a catastrophe. So we can see the duck curves that we have to expect in future, but there is solution to that as well. Then we have got consumer participation. Most of those smart grid programs across the globe are basically aimed towards enabling the consumer, because consumer was used to be in the last of that chain. Now that pyramid has been toppled. So more facilities or more functionalities to consumer will enable the very success of any smart grid program in the world, right? So also we have got operations. Now the operations will not only be in the realm of the very operations that we are accustomed with. It will be subjected to all the generation, transmission, distribution, automation, consumers, market, metering, recording, controlling operations. Without going into the detail, the very thing that we are basically looking at is the privacy and security issue. No doubt, smart grid is a very good thing. Everyone is very much into this concept. But the only Achilles heel of that smart grid is the privacy and security. Means anyone in our neighboring country or anywhere else can hack, for example, the grid if it's not secured properly, and can start any kind of or stop any kind of machines or whatsoever it is. So it will also be a catastrophe. And also in future, the more of the wars will be more of a cyber nature rather than direct attack. Anyways, then we have got markets. The markets, the deregulated ones, and the service providers. The service providers basically those people who are basically providing services for the net metering or installation of PV systems. What are they? They are also the service providers. So there will be new avenues in terms of hardware, in terms of software, in terms of forecasting or any kind of services that would popped up due to installation of this concept. Means basically, whenever there is a new thing in the market, it's not only accompanied by one or two aspects. It's accompanied by a whole functionality of aspects which further give way to further avenues. Whether you have, for example, we don't have demand response right now. We don't have demand side management. What are the reasons? We don't have that much bandwidth. We will from where we will arrange that bandwidth. First thing. The second thing, where we will share that we will save that data. There is a that data center is also subjected to various high percentage of carbon footprint. For example, in Pakistan, if you make a data center and still your generation is 65% thermal, so 65% of your generation will be fed to that data center. So indirectly, it's contributing to further carbon footprint, right? Anyways, we have got also, for example, demand response. Right now, it will be just, it's a concept. The practical application of that concept will be just like what a broker do to you in the stock market. On your behalf, he will, a broker can means buy or sell the shares. So in demand response, rather than moving towards the granularity or the small, what I say, every or if they say some kind of incentive based information, so you can give your rights to the demand DR aggregator, and it will on your behalf will go for either incentive based or price based incentives for your disposal. So let's move towards a smart grid package. So when we talk about smart grid, it's not just a grid that is smart. It includes technologies and functionalities. Technologies which are new, functionalities which were limited in the previous concepts. Then we have got most modern distribution concepts. I'll go through them one by one. And to make them work, we have got policies, work maps, pilot projects. Means jo dikhta hai, wo bikta hai. So once you have got a demonstration, then it will move ahead. So then we have got real world optimization, and real world optimization will always be multi-objective. It will not be a single objective. It will be multi-objective. Anyways, since the charity begins at home, so is the concept of smart grid. So you can see that we have got a whole defined electrical boundary and the communication boundary in this system. We have got AC, we have got DC, we have got loads, we have got generations, we have got storage, which acts both ways. When the frequency is less, it will start discharging, it becomes a source. And otherwise, it becomes a load. So how you will schedule them, all those things. So it's a whole thing in it's a whole universe in its own. Further, this concept accumulates to the concept of smart building. For example, we have got Centaurus. In the at the ground floor, we have got commercial area, and at the upper side, we have got residential area. How you will manage them? The tariffs would be different. The working would be different. How the power management will be enabled, right? Then we have got microgrid, the iconic microgrid with defined electrical boundaries. Let me give you a fun fact about the microgrid. The microgrid basically popped up, the concept basically arose from 1965 blackout in USA, from where the reliability basically comes to its very form that we are seeing it today. During that time, there was some island sort means there was one generator which was not shut down and it was providing load to its surrounding. So the people thought that why not we can use that kind of arrangement when the grid is out, or it can be, if the technology allows, it can be grid connected. So from there, this concept started. CERTs basically take lead in that kind of Microgrid installation and the pilot projects. And the very dimension, as since I'm a planning engineer, I would go for the topology of the Microgrid, and that too the interconnected topology, which is deemed to be both reliable and interconnected in the retrospect. Then we move towards virtual power plants. Now, what's the difference between a Microgrid and a virtual power plant? Microgrid has a defined electrical boundary, no doubt about that. It can be grid connected, it can be isolated. Virtual power plant will always be grid connected. Rather than providing power from one big generating unit, a small clusters of distributed generations can fulfill that demand. And the innovation on the hardware side will be more seen in terms of this Microgrid. But the modernization on the ICT side will be more visible on the virtual power plant kind of arrangement. Now it can be either low voltage, medium voltage. Usually Microgrid is low or medium voltage, right? Virtual power plant can be medium voltage or high voltage. Both are possible. Then the concept, the amalgamation of all those concepts in a city. I'm not talking about the smart city that you heard in the advertisements. Smart city is a concept in which all those things, whether you have got smart homes, smart buildings, smart neighborhoods, from the scale of smart home up till upwards, you have got all those things. That is smart city. Now, first of all, to solve a problem, you must see what are the issues. If you are quite familiar with the issues, it will be easy for you to solve that problem. So what are the issues at hand? Now the generation percentage has increased. As you can see, we have surplus generation and we have low demand. And still the shortage persists due to weak transmission network. So although we have worked with Lahore to Mitiari HVDC, we still require strategic reinforcement. And when I talk about strategic reinforcement of the transmission lines, it must not exceed 400 kilometers. If you exceed it from the 400 kilometers, the power amplicity and power carrying capability will reduce. Then we move to the net metering. So net metering, no doubt, is a very good, very phenomenal thing that we have observed in our lives. This Pakistani nation as a whole is very good in terms of embracing technology. We had load shedding, we started go for the UPS. When we have seen the potential, we have gone for the net metering. Now, net metering, the percentage is getting high. How to accommodate them? How to let this percentage go increasing? Right now, there is only net metering. What will happen when you have got electric vehicles? It will be a surplus. And for example, due to shortage of gas and other things, there are new gadgets in the market in terms of solar geyser, totally electrical geysers, electrical stoves. What happened then? How you will feed all those things? And remember, they are non-linear in nature. Right? So this is another one, how to start with smart grid technology to address that. Then as per ARE policy, 25% by 2025 and 30% by 2030. Respectable Sir Tosif H. Farooqi, who is Chairman NAPRA, has done a phenomenal job. He has included the hydel in to the renewable as well, so that we have reached up to this thing, that 30%. We are surplus 32 to 33% now, if we consider hydro as a renewable. But by 2047 or 2050, we must have 50% of the share. How we will add them, or how basically the 65% thermal and 35% of the others will be all the way around. What are the strategies? Since Rome was not built in a day, so will smart grid not will not be built in a day. It will be in a process of pipelining, scheduling kind of arrangement. So you can see the whole renewable that is at our hand. If we talk about wind and solar only, they only make 5% of our whole energy mix. You can see this is the hydro, the lower part, and this orange fellow is totally thermal, right? And these are the other technologies that we want to increase, basically the green ones and other ones. Now, Ministry of Energy says that we can consider AMI to help reduce distribution losses, as respectable sir has just shown you that he has done a phenomenal job in addressing those issues. So by 2019, we have got the total energy that was purchased by was 113 terawatt hour and sold was 94. So the aggregate technical and commercial losses accounts up to 17% in 2019 and 20, which are now 20%. So the very basic principle, that is generation is equal to load plus losses. So if we generate 20% or we purchase 20% to just meet those losses, where we are. If somehow we reduce it to half, 2 or 3 cities like Pune and Islamabad can be fed easily, right? So you can see the percentage of losses, although ISCO is very better in terms of performance, but the performance is not good in the other discourse. And also the safety issues are very much problematic. In those past years, 2017 and 18, there was used to be 1 death per day. Life is so priceless, right? So how to basically save the lives of the people as well? That's another issue, because we also usually ignore safety as well. Then we have got EVs right now. Battery electrical, right now we have got this hybrid electric vehicle. You are more very much familiar with the Prius, Toyota Prius, right? But plugged in hybrid electric vehicle or battery electric vehicles, they will make up to 40% by 2050, at least. I'm quoting the figures from the Ministry of Economics. Now the gap analysis and opportunities. Where there is a gap, there is opportunity. It's just based on your perspective, whether glass is half full or half empty. We will see that it's half full and how we can fill the other half. So first of all, the transmission system, its roadmap has been formulated by NAPRA and DDC and other stakeholders. And it started from February 2019 and up till 2020. It will be put forward in 2022 for final approval. So all those contingents, they have considered even the future requirements as well, that how we have to strategically reinforce that. Then we have got stakeholders, which include utilities, policymakers, technology providers, researchers, and consumers. Everyone has part in it, right? So being a researcher, I have to come up with a good idea that can be beneficial. You being students can make some good projects, which can result into some kind of Okay, sir. Okay, sir. 5 minutes, sir. Anyways, so what are the reforms? What we can do basically? Uh, the ICT and network necessities, as I said, that the data is something that is very problematic. So how ICT issues will be solved, data management and analytical competencies, forecasting optimization model, modified business model, qualified people, tested policy, and other support with a renewable penetration. So the EV policy, uh, the draft zero says that even your transport sector will be 30% by 2030. That will be additional load on your grid basically. And who will be responsible for providing charging? Whether you will allow third-party charging or utility will charge it, right? So the main things that are very important for that are the research and development and all those programs that I've written over here. And also this renewable, this EV, it must be charged via renewable, not via thermal-based electricity, right? Then we have got now the P2P technology, peer-to-peer. I'll just give you rather than going into that detail, just kindly go on the net, Google Power Ledger Australia. How you can use blockchain and peer-to-peer technology to increase the PV renewable or to make a virtual power plant for its better management, right? Because I have only 5 minutes to pack it up. So I have to just be quick for that. So the research questions are, there will be 5 million new houses expected. New non-linear devices, reactive power compensation issues, and new loads in the national grid. So what's the impact on surplus generation? Impact of reducing load, because our load factor is reducing. That's an alarming issue. So storage types in various smart distribution mechanisms like green hydrogen. Tariff of storage system, we have not considered storage tariff right now. It's not given. If someone wants to invest in the storage, what's the tariff for that? Right? How to run additional devices on grid and EV load control. So right now we have got a national grid. Only in Karachi, we have given just 220 kV lines to the Karachi K Electric. Rest of whole our grid is national grid. Now we have got two routes, eastern route and western route for the CPAC. So all the generation that has been allocated is basically for the CPAC. When the project will start in full swing, we will back to square one because all the generation will be given to them, not to us, to the public. So how to solve that? Now there are two options. There is one option. One option is this, that this is our eastern route, which is very close to our current transmission system. Why not we segregate whole Pakistan into 5 grids, virtual power plants or transmission systems, starting from Gilgit-Baltistan, KPK, Balochistan here, Punjab here, and Sindh here. It will be a much better in terms of power management. And these are the microgrids. These guys over here are wind microgrids, and these yellow ones are solar microgrids. To tap the renewable, their potential, why not we can make this thing? We can sell to here. We can exchange to other provinces via their transmission systems, right? Then we have got this thing, that how it will be completed. It starts from research, then you have some development, then you have pilot demonstration, feedback, and deployment. These are the standards you kindly go through for the enabling of this infrastructure. So the way forward is, I will give all the data from where I have taken this thing. This ARENA roadmap, the synthesis report, it starts from enabling technologies, business model, market design, and system operation. Every technology that we are basically working with must go through this whole procedure, right? Then we have got smart grid technology, need for those projects, the procedures. This is a generic cost to benefit analysis methodology that you will apply for every technology that you are working with right now, right? So I just move forward quickly. The EV, how we will basically, how long and how much the vehicles are there, at which time they must be charged, when it must be charged. Basically, I made this presentation from the perspective of enabling students rather than experts. So the students kindly go through this thing one by one. All the details have been given over here for their advantage. So the green hydrogen, how we can use it, what are the implications, and how can we move forward for that. Means we can store the surplus electricity into hydrogen, and when we need it, we can use that 20-80 ratio of hydrogen in the methane at our disposal. And this is the economic viability. Whenever you do any kind of economic analysis or financial analysis, kindly go through this net present value and all those things. They will be very phenomenal for you for doing any kind of project or any kind of study. So this is a Pakistan contribution in NDC renewable target across 2050. I'll just move forward. So these are the new technology horizons. First, see your limitations, then how you can enforce them, what are the roadmaps in the world, how you can tailor made for Pakistan, and how to apply them in terms of a scheduled layout. So future targets, right now, this is our system, this is our load, and these are our losses. So subjected to means we have, if we just divide those, the whole Pakistan into 5 virtual power plants to ensure our western and eastern CPEC routes, we can enable 40 to 50% generation across 2050. Losses minimization although varies. In some, in Punjab, it will be more, and other it will be less. So transmission losses can be reduced to 2%. Right now, those results have not been published. They are under review, and one has got a minor revision. So that's why I have just shown these values. So circular debt can ideally be 0 by 2050. Ideally be, what will be the reasons for that? And RG penetration will be 50%. And these are the conclusions. Ji, sir. Okay. The conclusion basically goes like this, that first of all, you must see that what are the limitations. Then what are the mechanisms? How those mechanisms can be addressed in different cases, scenario basis, right? Then try to add other factors like EV, like nonlinear load, other kind of things. So EV and battery, megawatt plus megawatt hour, that's the flexibility. How we can increase the flexibility. That's another thing to address with. Then we have got the storage. Hydrogen is something that is the world is very much after right now. So I don't know right now anyone has given any policy on hydrogen or not, hydrogen storage basically. So the ambitions also this 1.5 degree, right now we are the signees of the Paris Accord. We have to reduce our emissions so that we must be within 2 degree less. So 1.5 degree is something we must target for all the sustainable projects. And we don't have any carbon credits right now. The Kyoto Protocol that used to ensure you carbon credits, if it somehow revives again in one way or the other, it will further incentivize another boost in these renewable projects. And then we have got blockchain, P2P, IoT system. Those students who are working on this thing, mashallah, you are on the right way. Kindly go for that. It will be a future. So those gap analysis will give you better strategies in terms of addressing those things. And I thank you all, and I apologize if I have tested your patience. Thank you very much. Any question? Sir,
How the existing transmission system can be made more flexible and smarter so that
Sir.
the existing transmission system can be utilized to the thermal limit, which is the maximum.
Yes, sir. I have just mentioned that, sir, that if we divide our whole transmission network into 5 different transmission networks, including tapping the renewable resources. If I show you, sir. Oh, sorry. Where is it? एक second, ये चला गया. Yes, sir. Sir, right now it's congested, no doubt about that. So it will be a sort of what I say, scheduled kind of thing. First of all, we have to reinforce this system, that is Balochistan. This is the microgrids that tap the wind and the solar potential over there. So when this thing will be formulated, or this thing will be made on ground, so there will be some of the load will be shed from the main grid. That's the first thing. Then even Sindh has applied for its own transmission network. And reinforcement, if I talk about reinforcement, sir. So, sir, for example, this area, this one and this one, these two areas, they require reinforcement in terms of short, what I say, medium length transmission networks for that matter. So if we basically, if this migrates, this thing will be basically reinforced together. The whole load of Sindh will be shed from the national grid.
So instead of converting the long transmission line into medium ones and introducing, installing substations,
yes, sir,
it would not be better to install the FEX controller?
Yes, sir.
So
We have done study, sir.
Sir,
Yes, sir. You are right, sir. Sir, usually the FEC devices, sir, we have basically installed at HUBCO, and in a few STATCOM and SVCs in FFCL, TGF, and Zorlu. They are basically private entities. We have not right now installed them in public entities because of the reason their price is very much high. And the best FEC device that is very excellent for Pakistan is UPFC. But its cost is phenomenally 3 times of that of STATCOM. So that thing will be what I say, short-term solution, but not the long-term. The STATCOM kind of arrangement, because the very much load that is basically increased in the Pakistani grid is due to reactive power mismanagement. Or almost 30% of the load is reactive power mismanagement. So how we will address that as well? To address that, even the Lahore to Mitiari, we have made the DC out of it, but we cannot control the reactive power into that. There is only the active power contingent. We still have to install the reactive power if we have to convert that. And there will be some issues in using that directly. So there is a big research fields regarding that. My group is working for that, sir. Any other question? Yes, sir. Sir.
Now I think its price is very not cheaper, but it's not that.
Yes.
At that time it was installed in Japan and US.
Yes, sir. Yes, you are right, sir. Sir, I have done a project for FFCL just on the basis of they gave me data, and I just try to sort out the solution out of that. Sir, still the FEC devices that I'm talking about, there is no tax exemptions on those FEC devices. That's the first issue. And second thing is, although I think you are relating it with the other technologies which have been reduced in terms of price, but still the STATCOM and those devices are fabricated by a very small number of what I say manufacturers. So if something is made in Alto University, so the free charges will be very less for the Europe. But when it will come to Pakistan, it will be double in price. And installation, commissioning is another thing to go with. and net present value will increase high, and internal rate of return will be reduced very much. So there is not, it's not a usually cost economic proposition to install it on a high scale. Okay, thank you, sir. ये अब डाटा रखना है, रख लिया वो, ठीक, थैंक यू।
We'll be back around 11:40. Thank you.